Okay, let's get started, please. So, who can tell me what we're talking about? Can anybody remind us where we are in the story? We're kind of at the beginning of the story, but this course is called Transcendental Functions. I mean, it's really pre-calculus. We, at one point, I think right when I arrived 16 years ago, they changed the title to Transcendental Functions because they wanted to say that you can take this course and learn something about. You know, it's not necessarily just a prerequisite course, but you can think of it as you know, it's got knowledge in itself, of course. Yeah, so we'll get up to transcendental functions eventually, but we're not near that right now. Where are we right now? Anybody remember? What did we talk about last time? Yes, Olivia.
We left off at 1.5 graphs, and we also did like the distance formula in 1.4.
Yeah. So we were doing one-dimensional things, and now we're doing two-dimensional things, right? Maybe the most important of them is graphs of equations, right? So graphs of two-dimensional equations. Two-dimensional equations, right? You have something like I think we finished with something like x squared plus y squared equals 1. That's a two-variable equation, right? And then you can talk about its solution set, right? All the points, right? You want the solution set is all the x, y that make it true, right? Let me give this thing a name. So I'm going to call it star. Call this equation star. So making the solution set is all the points that make star true, right? And then you put those things on a plane, and that's the graph of your equation, right? So in this case, it turned out to be a circle of radius 1, centered at the origin, right? This is the graph of the equation of star, right? Okay, so that's where we are, and so today we're going to be talking about maybe the most simple kind of graphs, which are graphs of lines. Graphs of lines. And it's something very simple, but it's actually something really important. Lines are kind of the way that human beings understand things, right? When you see somebody running and you make an estimate as to where they're going to be in a couple of seconds, you're using some sense of the linearity of their motion, right? Like they're traveling a certain rate per time. Right, and you're saying, okay, they're going to be at this point. There's something built into the human brain that likes linearity, and that's kind of cool, and it's also kind of dangerous because if it's not linear, then it's a little bit hard for us to understand viscerally. Okay, so graphs of lines. You all know what a line is. It's kind of hard to define, but you all know what a line is. It's something that's it's one-dimensional. It's straight. It goes on forever in both directions. Right. It doesn't have any curving. Right. How do we describe a line? How do we describe a line? Right, using equations, using an equation, right? If you're Descartes and you've suddenly realized that everything in the plane can be described in terms of coordinates, maybe the first thing you would think of is, well, okay, if everything is coordinates, how do I describe a line, right? How do you describe a line? Right. Probably you've seen ways of describing lines. What are ways that you know of describing lines? What are ways of describing lines using equations? How would you describe it? Yeah, Amelia.
Slope.
Slope. Okay, so you can say like, we talk about something called slope, right? Right, which you probably heard it probably defined as like the rise over the run, right? Something like that. Yeah.
Also x and y intercepts.
X and y intercepts, right? So you can look at x and y intercepts, right? So if we're on a graph, right? If we're on a Cartesian, if we have the Cartesian coordinates put down, right, you could say, well, let's look at the x-intercept and the y-intercept, and those things determine it, right? So you could say, like, how do you tell somebody what line you're talking about? You could say, well, I can give that person the intercepts, and that's enough to determine the line, right? Right. So, what about equations, right? There's some equations that you probably have seen before to describe lines. Anybody? Yes.
Y equals mx plus b.
Y equals mx plus b, right? Y equals mx plus b, right? There's some other things that you've probably seen, this so-called slope-intercept form. So this is the slope-intercept form, so-called slope-intercept form. There's the so-called point-slope form, etc. And there's something called the general form. I'll talk about these. I'll explain what these are in a second, in case this is your first time seeing it. In any case, so let me see if I can talk about this question, like, how do you describe a line using an equation? Right. So here's one way you might think about it. So how do you get an equation? How does one get an equation from or for a line? How does one get an equation for a line? So here's one way you might think about it and say, well, like, I'd like to describe this line using an equation, right? I'm Descartes. I'm not really Descartes, but I pretend I'm Descartes. And I'm like, okay, I want to describe this thing using coordinates, right? So let's see. If I choose a point, let's just pick a point on the line and call that x naught, y naught. Okay, that's gonna help me. Then I'm gonna choose an arbitrary point, x, y. Okay, and I want to know, like, I want to be able to say this x, y lies on the line. This x, y lies on. I want an equation for this sort of general point x, y. Right. So, like, how do we describe this arbitrary point on the line? Right. So, like, this xy is any point on the line, right? So it could be, this guy. This is another xy, and this is another xy. All these guys, I want some sort of condition that says you're on the line. Okay. So here's how I think people probably thought about it. Almost definitely, they thought about it geometrically. They said, okay, well, let's draw. So here's our coordinate system. Right? Let's draw a parallel line this way, and let's draw a parallel line this way. So parallel to the axes, right? One line parallel to the x, one line parallel to the y. Right. Right. And here's another xy on the line. I'm going to do the same thing, parallel lines like this. Okay. So what do you notice about so here you get this triangle, and here you get this other triangle, right? And if these guys are on the same line, what do you notice about the triangles? If this xy is on this line, and this other xy, and I call this guy x prime, y prime, is also on the line, what do you notice about the triangles that are formed this way? Yes, Isa. They're similar, right? They're similar because you've got parallel lines here, right? You've got parallel lines, right? You've got parallel lines, and this line cutting through the parallel lines. And so you know from your geometry, that these angles are the same, right? You've got two parallel lines and a line cutting through it. So some rule of geometry says these guys are the same, right? And so you see that and this angle is the same. So these two triangles have the same angles, right? Right. So they're similar triangles, right? So so notice similar triangles. Similar triangles. And what does that tell you? That tells you that this thing here, the ratio of this to this, is the same thing as the ratio of this to this. Right? The ratio of this height to this length is the same as the ratio of this height to this length. Right? And that's going to happen wherever I am. Yeah, as long as I take a point on this line, I'm going to get that same ratio, right? So, you know, x, let's say, this thing, y minus y naught over x minus x naught is constant for all x, y on the line. Right, so here's what we observe, right? Right, that thing is constant, right? Whatever point I take on the line, I can play this similar triangle argument and say, well, I'm going to get the same number. That ratio is going to be the same for, you know, as long as I'm on the line, that ratio is going to be the same thing. Okay? That ratio we call the slope. We call this the slope of the line. Right? It's like every line has this magic number, right? Every line has this magic number. Let's call that thing the slope. The magic number we call that the slope. And you see why people say it's the rise over the run, right? It's like how far the thing rises over over the length and time, like over how much distance has passed, right? So this much distance has passed and it's risen this far. Right, so that ratio is called the slope, and usually denoted by b. Is a constant. I'm sorry, usually denoted m. Usually denoted m. Why is it denoted m? I don't know. Yeah, we usually use constants at the beginning of the alphabet. M is right in the middle of the alphabet. But anyway, people call it m. You know, when I was in graduate school, I had a professor who would say things like, suppose we have a manifold B, and he would write up a big M or something like that. And we all kind of, laughed at him and, said, oh, his mind is going. And now I see I am that professor. Right, like, we call it B, and I write up an M. It's M, so slope is M. Okay, so, right, so what do you see that, what's the point here? That this thing is a constant, right? That for a fixed line, every point on the line for a fixed line with slope m and with passing through the point x naught, y naught, every point on the line, every point xy on the line satisfies x minus x, y minus y naught over x minus x naught is m. Right? That's what we're seeing over here. Whatever point is on the line it's going to satisfy, it's going to be, this ratio is going to be some constant m. Right, I'm just saying the same thing again. For this fixed line with slope m passing through x naught, y naught, every point x, y on the line satisfies this. And so you usually write this as, so the equation, y minus y naught equals m x minus x naught. So I'm just going to multiply through. Y minus y naught equals m x minus x naught describes, describes the line. Okay, and this is the so-called point-slope formula. Right, so this is the point-slope formula. Okay, so right, so at this point you'd be pleased if you're a Descartes. You'd be like, okay, I figured out a way to describe lines in my coordinate world, right? I've just introduced coordinates onto the plane, and now I can actually use it to describe lines, right? Right. So right. Okay, so like, so for example, right, if a line passes through, let's say, 2, 3, a point 2, 3, and has slope 2, right, then, so it would look something like this, 1, 2, 1, 2, 3, right? So here's the point it passes through, and it has slope 2, which means that, every time you move over 1, it moves up 2, right? So every time you move over to the right, it moves up 2. Every time you move over to the left, it moves down 2, right? So something like this. Right? If you have this line, then what's its equation? What would the equation be for this line? The line that passes through 2, 3 and has slope 2. Write something down. Take 30 seconds and write something down. Okay, turn to somebody nearby and talk to them. What did you write down? Okay, would somebody like to tell me what they said? Yes, Phoebe.
Y equals 2x minus 1.
Y equals 2x minus 1, and how did you get that?
I kind of just visually, or so 2x comes from the slope of 2, and then I got -1 by following like the slope down the line until I got to the y-intercept.
Oh, okay. So you said, well, look, if we step over one more, we're going to go down 2, and so we'll be at -1 at that point, and then you use the slope-intercept formula. Okay, that's fine. What about if we wanted to do it? What about if we wanted to use this point and this point and this slope using this kind of equation? That's fine, but I want to. I sort of want to wean everybody off of the points of the slope-intercept formula, because I know you all are sort of trained to change everything to point into slope-intercept formula, and there's no real reason for that. Like other forms are also fine. So what if we wanted to use this? How would we do it? Anybody? So let's think, right? Same kind of thinking, right? So if this is an arbitrary point, right, xy, right, we know that y minus, so this point here is 2, 3, right? We can just write it down here. So y minus the y coordinate, right? Y minus the y coordinate equals 2x minus the x coordinate, x minus the x coordinate. Okay. Okay, so you can just write it down. You can write it down directly from this point and this slope. And Vivi, what you just did is fine, but you see that this actually is a bit faster because you already have the point and the slope. Why not use the Pointslope formula? You had to do a little bit of thinking to figure out where the y-intercept was. If it were more complicated, that would be sort of unnecessary effort. Does that make sense? Is everybody okay with that? Anybody confused by that? Right? Like if I if I give you another point, say pass it through 1, 5 with slope 6, slope pi, say. What would be the equation for that? So line through 1, 5 with slope pi. Can somebody just look at it for 10 seconds and see if you can just give me the Pointslope formula? Turn to somebody next to you and say, this is the formula. Okay. What would the anybody want to say? Oh, Fern, yes.
Y minus 5
Exactly. Right. So if you've got the point and the slope, and somebody wants the equation, you can write it down easily. Okay. Right. Right. And so yeah. So if your point is the y-intercept, right? So suppose we did have this thing. So it'd be like your point is 0, -1, and slope is 2, right? What would be the equation in that case? Well, it would be y y minus -1 is equal to 2x, right? 2x minus 0. Actually, let me make it a little bit more appealing. Suppose you have the intercept and it's 0, b, and you know that the slope is m. Right. In that case, you see that the equation is going to be y minus b is equal to m x minus 0. Right? Everybody following? Right? Right. And if you rearrange things, you see that this is going to be y equals mx plus b, the so-called slope-intercept formula. Slope-intercept formula. Right. So right. So the slope-intercept formula is just the point-slope formula. It's just the point-slope formula if you know if your point is the y-intercept. Okay. So okay. So they're basically and you can take forms and then change them into different forms, right? So like if I have this form here, right? This is y minus 3 equals 2x minus 4. In other words, y equals 2x minus 1, right? So you can take the point-slope formula, you can take the point-slope formula, and then just move everything to the right side and change it into the slope-intercept formula, right? So it's easy enough to move back and forth, but these are all basically the same thing. Okay, these are all basically the same thing. These are ways to describe lines. So there's basically three ways, three different forms. One is, excuse me. One is, sorry. One is this, point-slope form. One is the slope-intercept form. And then the last is so-called general form, where you move everything to the left and just rewrite it as some constant times x plus some constant times y plus some constant equals 0. Right. These are all the same. They're all describing lines. It's just you've shifted the form. Right. So they're just different forms of the same line. Different forms of equations describing the same line. Right, and you see that you can go from one form of the equation to another form of the equation, right? And if I wanted to change this into general form, I would just move everything to the left, and say negative 2x plus y plus 1 is equal to 0. Right, that would be the general form. Right, this is slope-intercept, and this is point-slope. So just be comfortable with knowing that these are all lines and that you can go back and forth between them. Okay. So why do we even have these different forms? Basically, each form emphasizes a different thing, right? So like if you see it in this form, you're like, okay, I know what the slope is and I know what its intercept is, right? What its y-intercept is. Right. If I see it in this form, I don't know its y-intercept offhand, but I do know a point that it passes through. Right? If I see it in this form, right? If I see this equation, I'm like, oh, okay, it passes through 2, 3. Right? That's nice, but just for that one point. Right? In this thing, I know that the y-intercept is negative 1. Right? I know that the slope is 2. Here, I know that the slope is 2. Yeah, this one, it's a bit more opaque, but it's I think maybe these forms are a little bit easier to get your head around. But so you can sort of read different information off of the different forms. Okay. Right. Yeah. So let's see. So, oh, I should say that these equations, there is one kind of line that these equations aren't so good for. Well, maybe these equations aren't so good for, which is vertical lines. If you have something like x equals a constant, and so this is a vertical line. In that case, it doesn't make sense to talk about slope, the slope of the line, because it's vertical, right? But those are easily described anyway, because so this is some line, right? Some vertical line passing through this point C, right? So you can't, you can't put that in point slope or slope intercept form, okay? But you can put it in general form. General form, maybe this is what's good about general form. It can apply to all lines, whereas these things only, can't handle vertical lines. Are you guys okay? Okay. Okay. Let's see. So let's see. Okay, let me give you a couple of exercises. First one is, so write down equations for the following lines. Okay, so first one passes through 0, 5 and has slope 6. Okay. The second one is vertical and it passes through, say, 3, 2. The third one is horizontal, and it passes through also 3, 2. And the last one passes through, I'm just going to give you 2 points on the line, passes through 2, 1, 2, 1, and 5, 7. So take maybe 3 minutes and see if you can write down equations that describe these lines. Okay, even if you're not done yet, talk with somebody nearby, and maybe you can work together if you're stuck on it, something.
Yeah, I would just sort of throw like C undefined, right? And then same with horizontal. Okay, I mean, I just, yeah. Yes, like I just write down. And then I chose what is I just sort of rearrange this. Yeah. I could also get with the other yeah, I did.
Okay, so let's talk about these. The first one passes through 0, 5 with slip 6. Somebody want to tell me how you got an equation for that? Zoe?
Yeah, I put in the Pointslope form.
Pointslope form? Okay.
So y minus 5
Mhm.
equals 6x.
Yes. So y minus 5 equals 6x minus 0, or 6x, right? Which is fine. And you see that, you know, if you had used slope-intercept form, because this is, you could say, another way would have been to use the slope-intercept form. This is the y-intercept. So you'd say, okay, this is y equals 6x plus 5, right? And you see that you can get from this one to that one, you know, pretty easily, right? This is 6x. You see that they're the same thing, basically, right? Okay, number 2, vertical through 3 comma 2. Anybody? Vertical line. Right. X equals 3. Thank you. Right. Pretty straightforward, right? You know that. Right. This is 3. It's everything where the x coordinate equals 3. The horizontal line through that point, so 3 comma 2. What about the horizontal line? What would that be? Y equals 2, right? Okay, what about the last one? Passes through these 2 points. How would you describe it? Stella?
So I found the slope doing, so I did 7 minus 1 over 5 minus 2.
Okay, right.
So I found that the slope was 6 over 3, which is 2. And then I guess what I did, I'm not sure if it's right, but I put it into the point slope form. So
Okay.
I did y minus 7 equals 2 times x minus 5. And then I got that it'd be y equals 2x minus 3.
So what did you do after that? You
So y minus 7 equals 2 times x minus 5 instead of 3.
Oh, I'm sorry, the slope was 2, sorry.
And then so I did y equals 2x minus 10 plus 7. And then y equals 2x minus 3.
Okay, so at the end you converted it to slope-intercept form. Okay, great. So, yeah. So, right, everybody okay with that? So you see that we have these 2 points on the line, right? We have 2 points on the line, so you can use them to figure out the slope, right? The slope is going to be the difference in the y values over the difference in the x values, right? So y2 minus 1, 1 over x2 minus x1. We know that ratio is constant. Right? So if you've got 2 points on it, you can figure out that ratio, and that ratio turned out to be 2. Right? So she figured out the slope and said, okay, now I've got the slope and I've got these 2 points. I can use either one of them in the point slope formula, right? So you could say, you know, she used the second one, you know, y minus the y value equals twice x minus the x value. Could also just as well have used the first one, so y minus 1 equals 2 x minus 2, right? That's also fine. So it's sort of like, I think the point slope formula is easy to use, right? If you've got a point and the slope, use the point slope formula. The disadvantage of it is that it sort of doesn't look like the same line, right? So you could have you could have an infinite number of ways of writing this line using the point slope formula, just using different points, and it sort of doesn't look like the same line. What's nice about maybe what's nice about these things is that there's just one possibility for it, right? There's just one possibility for the slope-intercept because you're choosing the y-intercept as that point. Or this one, there's just one possibility for it. So you can tell easily if you've got exactly the same line. Everybody okay with this? Yeah. Close your eyes for a second. Raise the finger if I should go faster. Raise the finger if I should go slower. Okay, thank you. Okay, so most people are satisfied, which is good. I actually am phenomenally bad at telling how you guys feel. With my own children, it's the same thing. I don't understand I think I always joke about it and say that I have very limited facial expressions myself, and so because of that, I can't really understand people's facial expressions. So I joke about it, but it's probably true. Yeah, I tend to use my ears more than my eyes. Yeah. Okay. Got 7 minutes left. There are a couple things there are a couple things left in this chapter. The first one is that some observations about slopes. So first, one, if two lines are parallel, then they have equal slopes. And that kind of makes sense, right? Because if you've got parallel lines, right? If you've got parallel lines, then when you make these triangles, right? So let me draw some. Right? So like all of these pairs of lines are parallel. Right? So these lines are parallel. These lines are parallel. Right? Right? What's going to happen? This third set of lines are parallel, right? What's going to happen is that this angle and this angle are the same, and this angle and this angle are the same, right? So geometry is going to show you that you've got similar triangles, right? And so because you've got similar triangles, that ratio is the same, so the slopes are the same, right? So it's just because you've got so many parallel lines everywhere. So that one's sort of intuitive. The one that's not intuitive is the one about perpendicular lines. Does anyone know about what happens if you've got two perpendicular lines? If two lines are perpendicular, then what can you say about the slope? Suppose they have slope m1 and m2. What can you say about the slopes, Janie?
Slopes are negative inverses of each other?
That's right. So you multiply them and you get a -1. Yeah. They're negative reciprocals of each other. That one is I don't know, maybe for some of you, maybe there's somebody in this class for whom that's intuitive. It's not intuitive for me. Let me sort of sketch out the argument. Suppose you have two lines and they're perpendicular to each other. Okay, suppose you got these two lines and they're perpendicular to each other. You can put a coordinate system on it. Okay. put a coordinate system on the plane like this. Okay. Let's say that this guy has slope m1, and this guy has slope m2. Okay, m2 is a negative number, right? M1 is a positive number. Okay. Okay. So then let's go out to. So here's my coordinate axes. Let's go out to a distance of 1 here. Okay. Let's go out to a distance of 1 and make triangles. Okay. So I draw a vertical line here. Okay. So let me kind of blow this up. Something like this. Right. This guy has slope 1. This guy has m1. This guy has slope m2. And this length is 1 here. This length is 1. What's the distance here? What's the length of that? The slope of this line is m1, and we moved over 1 step. So how far up have we gone? Not 1. We've gone to the right 1, and how much will it rise during that time? Yeah, the slope, so m1, right? So that length is m1 here, right? Okay. Now we've got this negative slope, m2, right? And we go over to the right 1. So this length is going to be negative m2, right? m2 is a negative number, so the length here is going to be negative m2, right? Okay. And then don't worry if you don't get this. This is sort of like enrichment. So then let's play the Pythagorean theorem over and over and over. So by the Pythagorean theorem, right? This is these little guys are right triangles, and this big guy is also a right triangle. Okay. So we just like go crazy with the Pythagorean theorem. So now go crazy with the Pythagorean theorem. So you know that this length is going to be the square root of 1 plus m1 squared. Right? You know that this length here is going to be the square root of 1 plus m2 squared, right? Negative m2 squared, but the minus vanishes. Okay. So then you use the Pythagorean theorem again, and you say, well, a squared plus b squared equals c squared, right? So a squared plus b squared equals c squared, right? Right? A squared plus b squared equals c squared. What's the square of m1 minus m2? Yes, Stella.
m1 squared plus m2 squared?
No. So you get m1 minus m2, m1 minus m2. Remember, if you multiply, you use the whatever you do, you get m1 squared minus m1 m2 minus m2 m1 plus m2 squared. Right. So you get m1 squared minus 2 m1 m2 plus m2 squared. Right. So you get 2 plus m1 squared plus m2 squared equals that. Okay. Okay, and you see what happens? What happens? Well, the m1 squared cancels, the m2 squared cancels, and you see that m1 m2, so negative 2 m1 m2 is equal to 2, right? In other words, the product of the slopes is negative 1. Right? Dividing both sides by negative 2, you see that the product of the slopes is negative 1. Okay, so this is how you might see that if you have got two perpendicular lines, then then the slopes are negative reciprocals of each other. Okay. You've probably seen this fact before, but maybe not the proof of it. So yeah, so what's kind of cool in this course is that the Pythagorean theorem shows up all over the place. The thing that we introduced at the very beginning in the Pythagorean theorem, actually, like, you know, a huge part of the course, a huge percentage of the course is actually falls out of the Pythagorean theorem, including this one. Okay. So let me turn this off. So